Hi, my name is Logan Lebanoff, and I am a student from the University of Central Florida. Today I'll be presenting a cascade approach to neural abstractive summarization with content selection and fusion. This is a joint work with collaborators from Adobe, Frank Dernancourt, Doosun Kim, and Walter Chang, and my advisor, Fei Liu. The most popular method for abstractive summarization is end-to-end neural models. However, these models require large amounts of data, and many domains lack these large data sets to train on, such as radiology reports, congressional bills, and meeting conversations. These end-to-end models also act as black boxes, and it's very hard to see the decision-making behind their generated summaries. This indicates that end-to-end models may not be a one-size-fits-all solution for neural text summarization. In this work, we aim to investigate the feasibility of a cascade approach to summarization. This is a pipeline architecture where we first choose one or two sentences from the source document and then highlight their summary-worthy segments and then use those as a basis for composing a summary sentence. We advocate for explicit content selection as it allows for rigorous evaluation and visualization of intermediate results. Another thing that we seek to improve with this cascade approach is sentence fusion. Specifically, when a pair of sentences are selected, it's important to ensure that they are indeed fusible. There exists cohesive devices that tie the two sentences together. So our cascade method of selecting sentences and words within those sentences is a step towards this better sentence fusion. I'd also like to point out that we have a couple of works dedicated to improving sentence fusion. The first is our dataset containing these cohesive devices that ties the two sentences together, presented at this year's ACL Student Research Workshop. And our work on learning to fuse sentences with transformers for summarization, presented at this year's EMNLP. So now I'll go over our cascade approach. First, on the left side is the content selection step, which selects sentences and highlights words within those sentences. Then the outputs of this model are sent to the information fusion model, which generates a summary sentence based on the selected sentences and the highlighted words. I'll go into the content selection step first. The input is a candidate sentence or pair of sentences from the article. This is sent to a BERT model to predict a score, which will represent how important the sentences are, and if the input is a pair of sentences, then how compatible the two sentences are. This step is necessary because without it, the fusion model may, in later steps, may arbitrarily stitch together text segments from unrelated sentences, and this can yield a summary with hallucinated content and incorrect facts, which we do not want. We extend this content selection model with fine-grained content selection. So this model creates a classification layer on top of each token, which will predict whether this token should be highlighted or not highlighted. And if it's highlighted, this represents that the token is important. This course-defined method allows us to examine the intermediate results and compare them with the ground truth. Next, these are sent to the fusion model. We use an encoder-decoder model, which generates a summary sentence from the selected content. The way we input the highlights is using an additional embedding. So there are two choices for the highlight embedding. It can be a highlight on or a highlight off embedding. The advantage is that it provides a valuable intermediate representation. It can be easily incorporated into encoder-decoder models like this and can be adapted to new domains. For training data, we use 1 million instances taken from the CNN Daily Mail dataset. The instances each look like this, where the input is one or two article sentences taken from the article, and the output is their corresponding reference summary sentence. These are collected using the same procedure from our previous work in 2019. This data is used to train both the content selection model and the sentence fusion model. Now let's go on to the results. Our models, Cascade Fusion and Cascade Tag, are comparable to or outrank several extractive and abstractive baselines. The Cascade Fusion model includes all three parts of sentence selection, fine-grained content selection, and fusion, while Cascade Tag has only the two content selection parts. When we compare our Cascade Fusion model to BERT Abstractive, we can see that our model significantly outperforms BERT Abs in Rouge scores. And what this shows is that course-defined content selection is necessary to guide the sentence fusion model to produce informative sentences. Now let's take a look at some example outputs. First, we have the reference summary sentence, which was written by a human for this article. And we also have the two article sentences that were used to create this reference sentence. Now, our model chooses these two sentences from the article, and these two sentences are salient and compatible. Our content selection model also highlights content, as shown by the blue and green regions. And these regions are important, and they also ignore a few unimportant phrases. Finally, these are passed to the fusion model, which then generates a valid sentence fusion, a valid summary sentence, which looks like this. The next question we want to answer is, how much should we highlight? So I'll do a breakdown of these two graphs. First, we're looking at how many words do we want to highlight from the article. So when we vary this, what effect does it have on the Rouge score? So on the left is Rouge 1, and on the right is Rouge 2. What common sense tells us is that if we highlight too much, then this can be unhelpful. As shown on the right side, this is reflected on the graph. If we highlight 90% of the words in the article, then we get very low Rouge scores. And similarly, if we go to the other extreme and we highlight too little, then this is also unhelpful and yields lower Rouge scores. So what we want is somewhere in the middle, and we want to find out what is that middle point. So first we explored three different methods. The first is thresholding, where all the words with score higher than a given threshold are highlighted. Second, we looked at if we select a specific proportion of the input article. And next is something similar, where we select a specific proportion of just the input sentence or pair of sentences. So what we find is that thresholding, as shown in the blue line, performs the best, as it gives the most freedom for content selection. An example of this is if the model gives high scores to many words in the sentences, then we should correspondingly highlight those many words. Conversely, if only few words score highly, then we should only highlight those few words. And thresholding gives us this flexibility. We also find that the best results come from highlighting 58 to 78% of the words of each sentence. This is much higher than what the fusion model was trained on, which is about 31% of each sentence highlighted. And so what this shows us is that when the content selector is not as effective, then it may be better to highlight more rather than less. In summary, we present a cascade approach to summarization that separates content selection from surface realization. Our approach makes use of text highlights as an intermediate representation. The generated summaries using our method are more interpretable, as you can see by the highlighted regions that are selected in the content selection step. And the content selection approaches for sentence selection and highlighting can be customized for domain-specific tasks. Thank you.